So, in the last couple of lectures we have been discussing the conformation of isolated polymer chains primarily. We have looked at the different models for ideal polymer chains describing the conformation, end to end distance and other dimensional properties of such chains. We also towards the end of the previous lecture briefly discussed the behavior of real polymer chains in solutions. So, in today's lecture we will be carrying forward our discussion of polymer solutions further, and today we will specifically focus on the study of thermodynamics of polymer solutions. So, studying the thermodynamic behavior of polymer solutions is important because it can help in the prediction of phase behavior of polymer solutions. Polymer solutions are widely encountered in many applications, and its the prediction of phase behavior is important in many applications as well. Further, a knowledge of thermodynamics of polymer solution can actually help in establishing or determining whether a given polymer is soluble in a given solvent or to what degree a given polymer dissolves in a solvent. Apart from that, miscibility in polymer blends is also something where studying the thermodynamics of polymer solutions in blends is important. So, let us look at the content of today's lecture, what we will be going through in the present lecture. So, we will actually begin by a discussion of thermodynamics of ideal solutions. So, before we move on to studying the thermodynamic behavior of real solutions and theory describing that, we will first start off by talking about the thermodynamics of ideal solutions, and specifically we will look at the how the expressions for entropy change of mixing or Gibbs energy change of mixing can be obtained. Then we will move on to the study of thermodynamics of polymer solutions, and there we will focus on a particular theory which came about in the early 1940s, but it's the beauty of this theory is that it's a relatively simple theory, but is still able to capture many of the qualitative features displayed by polymer solutions. So, we will study this theory which is known as Flory-Huggins theory. So, we will study the thermodynamic behavior of polymer solutions within the framework of this Flory-Huggins theory, and in this lecture we will only partly be covering this theory, and in the next lecture we will complete the discussion on this theory. So, in today's lecture we will specifically focus on using this Flory-Huggins theory to determine what is called combinatorial term and calculation of certain quantities, as well as calculation of a particular component of the entropy change of mixing. So, we have a few symbols here which might not be very clear right now, but by the time this lecture ends I hope that all the symbols and the meanings will be clear. So, before we move on, let us just briefly look at the nomenclature that is relevant for today's lecture. So, many of these symbols we have already discussed in the very first lecture on introduction to polymers. There are some new symbols, specifically symbols related to thermodynamic quantities. So, symbol for enthalpy, the standard symbol is H. So, Hi will represent P of a particular component I. Similarly, Si for entropy of I, Gi for the Gibbs free energy of component I in any mixture. Further, we are talking about polymer solutions which are actually mixtures. So, we will be focusing on quantities like enthalpy change of mixing, which will be represented by delta Hm. Delta Sm will represent the entropy change of mixing, and delta Gm will represent the Gibbs energy free energy change of mixing. T of course will stand for temperature. This symbol X will be using this symbol to denote the number of segments in a given polymer chain or polymer molecule. So, again when we discuss the Flory-Huggins theory, the what is meant by a segment of a polymer molecule, that will become clear. Apart from that, the Avogadro constant, Boltzmann constant, universal gas constant, these are the standard constant that we will come across during our discussion today. So, let us begin. Before moving on to studying the behavior of polymer solutions, let us begin by the simplest case, which is that of an ideal solution. So, let us see how how one can basically derive the basic equations for change in entropy and Gibbs free energy change of mixing for ideal solutions. So, an ideal solution, and the definition of ideal solution can be a solution where the components being mixed are of the same size, or pretty much the same size, and the interactions are also almost identical. So, what we mean by identical interactions is that the interaction, let us consider for example, a binary solution or a binary mixture where we have two components. Let us say the component 1 is the solvent, component 2 is the solute, and when we mix the two to form the solution, then in an ideal solution the interaction between molecules of type 1 will be similar to the interactions between molecules of type B or type 2, and the cross interactions between molecule of type 1 and molecule of type 2, that also will be similar to the like interactions between 1 or 2 molecules. So, all the interactions will have similar strength. So, an ideal solution basically again is where the interactions are similar and sizes are also similar. So, from thermodynamic point of view, an ideal solution is defined by a solution whose formation actually does not lead to a change in enthalpy and a change in volume as well. So, both the enthalpy change of mixing and the volume change of mixing denoted by delta Vm here. So, both of these quantities are actually 0 for an ideal solution. So, since the sizes are identical when the components are mixed, then sizes being identical and there being no difference in interactions, the volume also does not change, and since the interactions are similar, the enthalpy also does not change upon mixing. So, the definition of Gibbs energy change of mixing is just delta H of mixing minus T times delta S of mixing. That is the standard definition of any Gibbs energy change or Gibbs free energy change. So, for ideal solution, since the enthalpy change of mixing is 0, the Gibbs energy change can simply be expressed in terms of the entropy change of mixing multiplied by minus T. So, now this Gibbs free energy change of mixing is an important quantity, and the thermodynamics of ideal solution as well as polymer solution, in both the cases what we will try to do is come up with an expression for this Gibbs free energy change of mixing, because once we have an expression for this, many other quantities like the chemical potential or the activity coefficient, such quantities can be determined starting from here. So, it is an important quantity, and our aim here is to establish relations for the Gibbs free energy change of mixing. So, since for an ideal solution Gibbs free energy change of mixing is directly related to the entropy change of mixing, here what we will do is first try to establish an expression for the entropy change of mixing. So, entropy change of mixing is basically defined as the change in entropy due to the formation of the mixture. So, for an ideal solution, although the enthalpy change of mixing, volume change of mixing are 0, the entropy change of mixing, as we will see, is not actually 0. So, entropy change of mixing is defined as the difference between the entropy of the mixture that is formed and the respective entropies of the pure species 1 and 2 which were mixed to form the solution. So, before we go ahead, for today's discussion, what we will need is what is called a statistical mechanical definition of entropy. So, this definition of entropy was provided by Boltzmann, and that is why this expression or formula for entropy is referred to as the Boltzmann entropy formula. So, what this expression states is that the entropy of a collection of molecules is basically Boltzmann constant multiplied by the natural log of a quantity omega, and this omega is nothing but the different number of distinguishable equal energy states or equal energy arrangements that are possible for this given collection of molecules. So, if we have a set of molecules or a collection of molecules, the number of different ways in which we can arrange these molecules with each arrangement being distinguishable from the other, but having the same energy. So, the number of such different states or arrangements, that is referred to as this quantity omega. So, this with this Boltzmann entropy expression, now what we will do is write down this the entropy of the individual components 1 and 2 as well as the entropy of the mixture in terms of this Boltzmann entropy formula. So, the S1 will be just Kb times ln omega 1, S2 will be Kb times ln omega 2, and S12 will be Kb times ln omega 1 2, where the omegas are again the respective distinguishable arrangements that are possible in the different cases that we have here for the pure components and the mixture. So, again the formula for entropy change is S12 minus S1 plus S2. So, if we substitute the expressions of these entropies using the Boltzmann formula, then we get the following expression, which again can be simplified to get an expression like this: Kb multiplied by natural log of the ratio of omega 1 2 by omega 1 multiplied by omega 2. So, with this expression in place, now all we need to do is come up with expressions for these three quantities omega 1, omega 2 and omega 1 2. So, if we have expressions for these three quantities, those can be substituted here and one can get a expression for the entropy change of mixing for ideal solution. So, to do that, let us first consider a model for this ideal solution behavior that we are discussing. So, the model that we will be using for further derivation basically is what is called a lattice model, and here what is assumed is that for whether it is a pure component or a mixture, all the molecules basically occupy distinct sites on a lattice. So, for such a kind of a model, omega 1 basically will be the number of different ways in which n1 indistinguishable particles or molecules of the solvent can be placed on n1 lattice sites or lattice cells. Similarly, omega 2 will be the number of ways in which the n2 indistinguishable molecules of the solute can be placed on the n2 different lattice sites. So, in our discussion we will represent the solvent molecules by this solid orange circle and the solute molecules by this empty black circle. And we say indistinguishable in both the cases, that is the word which has been highlighted here. So, we say that in both the cases the molecules are indistinguishable because the molecules in both the cases correspond to those of pure components. So, for pure components all the different molecules will pretty much be indistinguishable from each other. So, in both these cases the N1 molecules in the first case of the solvent and the N2 molecules in the second case for the solute, they are indistinguishable. Now, if we mix N1 molecules of the solvent and N2 molecules of the solute, then we will form a mixture containing N1 plus N2 molecules, and the lattice model that we are employing or will be employing basically requires that these N1 plus N2 molecules of the mixture of the solution are placed on N1 plus N2 lattice cells or lattice sites. So, representation of a typical lattice of the mixture or solution that is formed, that is shown here. So, here we see that the molecules of the solvent, that is the solid orange circles, and the molecules of the solute are kind of randomly distributed over the different lattice cells. And for simplicity we are showing a 2-dimensional lattice. In reality, of course, the lattice will be 3-dimensional. So, here we are showing a square lattice. The actual lattice can be cubic in 3 dimensions, or it can have any other shape as well. So, so now that we have defined our lattice in this way, the two things that we can directly notice is that the omega 1 and omega 2 will be 1 each. The reason for that is that omega 1 and omega 2 correspond to the number of distinguishable arrangements of the pure solvent molecules and the pure solute molecules, but all the pure solvent molecules are identical. Similarly, all the pure solute molecules are also identical. So, if we want to place N1 identical solvent molecules on N1 cells of any kind of lattice, then there is only one way to do it. If we try to let us say swap two different molecules here, then we will not end up with an arrangement that is distinguishable from the previous one. So, essentially there is only one way to place N1 identical molecules of solvent on N1 cells of a lattice. Similarly, for solute also we have N2 identical molecules of solute. So, on a lattice containing N2 cells, there is only one way in which they can be placed. So, again the number of arrangement is 1, and so omega 1 and omega 2 are both unity. But for the case of mixture, actually the situation is different, because now all the particles are not actually identical in the solution or the mixture that we have. We have both solvent molecules and the solute molecules present, as shown in the representative lattice here, and there are actually, because there are two different types of molecules now, there are many possible ways of arranging these molecules on these lattice cells. So, the omega 1 2 in this case is actually not 1, but it is given by this kind of an expression. So, omega 1 2 for this case is given by n 1 plus n 2 factorial divided by n 1 factorial times n 2 factorial. So, the numerator here in this expression, the numerator here n 1 plus n 2 factorial basically provides a different number of ways in which one can place n 1 plus n 2 of these molecules on n 1 plus n 2 number of cells in our lattice. But if we consider only the numerator, we are actually overcounting the number of distinguishable arrangements, because even for a mixture of or a binary mixture placed on the lattice here, there are many arrangements out of the n 1 plus n 2 factorial arrangements that we have counted. There are many arrangements which will actually be duplications, or in other sense which will be indistinguishable from each other. So, this the denominator contains n 1 factorial and n 2 factorial, these two terms. These two terms basically take care of the fact that if we consider just n 1 plus n 2 factorial arrangements, we are over counting, and we are actually counting many arrangements which are actually identical. So, that scaled by these two quantities, and we get the overall number of arrangements in the case of mixture. So, to further illustrate this point, let us consider again the lattice that is shown here, and here let us say if we swap any two molecules of the same type. So, let us say we swapped two molecules of the solvent, these two. So, after swapping we see that the arrangement of the overall lattice remains unchanged. So, because we have n 1 identical molecules of the solvent on the lattice, this n 1 factorial terms come into play here, because these n 1 solvent molecules, their internal swapping and rearrangement basically will not lead to any change in the overall arrangement. So, the n 1 plus n 2 factorial, this term has to be divided by n 1 factorial. Similarly, if we consider any two solute molecules and let us say we swap them. So, we in this case we have swapped these two molecules, and again we see that swapping any two randomly chosen solute molecules also does not create any new arrangement. So, to account for such identical again cases resulting from the swapping of different solute molecules, this n 2 factorial term also has to be considered here. So, overall the omega 1 2 term is represented by a ratio of n 1 plus n 2 factorial and n 1 factorial times n 2 factorial. So, if we now substitute all the expressions for omega 1 2, omega 1 and omega 2 in the expression for entropy change of mixing, then we end up with this expression here. So, we see that the expression that we have obtained here contains factorials of different terms. So, next what we will see is that in the case of n 1 plus n 2 factorial or n 1 factorial n 2 factorial, these terms, there is an approximation that can be made provided the numbers n 1 and n 2 are quite large. So, this approximation is referred to as Stirling's approximation. It is valid for cases where n is large. So, what it states is that the natural log of n factorial is approximately equal to n times ln n minus n, provided n is large. So, in a typical scenario for a given solution, when we are mixing two substances, the number of molecules usually will be very large. So, n 1 and 2 are large quantities. So, typically the Stirling's approximation will be valid. So, now let us apply the Stirling's approximation to the entropy change of mixing that we have derived just now. So, we can apply Stirling's approximation to all these terms. So, we have three terms containing natural log of factorials. So, and in all these terms the quantities n 1, n 2 and n 1 plus n 2 are quite large. So, Stirling approximation can be applied to all of them, and if we do that, then the expression for the entropy change of mixing gets simplified like this. And now here we see that this minus n1 term will cancel this plus n1 here, this plus n2 will cancel the, or this minus n2 again will cancel this plus n2 here. So, cancelling these terms and again simplifying and rearranging, in the next step we can say that the entropy change of mixing can be represented by this equation here. Now, this term here again we can split into two terms. So, it is n1 plus n2 multiplied by ln n1 plus n2. So, we can write it as n1 ln n1 plus n2 plus n2 ln n1 plus n2, and we can split this into two terms and then combine respective terms with these two terms. So, splitting in splitting can be done in this fashion. So, we have one term here and one term here, and this term will be combined with this, and similarly this term we can combine with this, because in both these cases n1 is common, here in both these terms n2 is common. So, we combine and finally end up with this kind of an expression for the entropy change of mixing. So, we see that inside the log we get these ratio n1 by n1 plus n2 and n2 by n1 plus n2, and as we know these ratios basically are nothing but the respective mole fractions. So, these ratios can be expressed as the respective mole fractions x1 and x2, and the expression for entropy change of mixing, as you see, has simplified to negative Boltzmann constant multiplied by n1 ln x1 plus n2 ln x2. And now if we want to change from the number of molecules n1 and n2 to the number of moles small n1 and small n2, then the factor of Avogadro number will appear. So, the number of molecules n1 will just be equal to the Avogadro number multiplied by number of moles n1 small n1. Similarly, the number of molecules capital N2 will be equal to Avogadro number times number of moles small n2. So, so now these two constants, Boltzmann constant, Avogadro constant, they can be combined together and their product is nothing but the universal gas constant. So, finally, upon simplification and combining constants, the expression for the entropy change of mixing that we get is that delta S of mixing is equal to minus R number of moles n1 times ln x1 plus number of moles of solute n2 times ln x2. So, this is the entropy change of mixing for an ideal solution, and if we just multiply this entropy change of mixing by minus T, we will get the Gibbs energy change of mixing, the expression for that, which is nothing but RT n1 ln x1 plus n2 ln x2. So, this is a standard thermodynamic result which one can obtain from classical thermodynamics as well, but here what we have used is the statistical definition of entropy and the concept of a lattice model to perform this derivation, because the same will be used in the case of polymer solution as well. So, we see that these mole fractions x1 and x2 will of course be less than 1. So, since these are less than 1, their natural logs ln of x1 and ln x2 both will be negative or less than 0. So, what that implies is that the entropy change of mixing will always be positive for ideal solutions, and the Gibbs energy change of mixing will always be negative for ideal solutions. So, with that introduction to ideal solution, thermodynamics of ideal solution behavior, let us now move on to the case of polymer solutions and see how the scenario is different there. So, let us consider the thermodynamics of polymer solutions. So, in this case, let us say that we have, again as we did for the case of ideal solutions, we will adopt what is called a lattice model, because the theory that we will be discussing for polymer solution, which is the Flory-Huggins theory, that is based on the lattice model of this polymer solution. So, here let us first consider component 1, which is the solvent, and let us say we have n1 molecules of this pure solvent, and that occupies a certain lattice. So, each molecule of the solvent occupy individual cells in the 2D square lattice that we have shown here, but as mentioned in the actual case we will have a 3D lattice, and here we have shown a square lattice whose 3D version will be a cubic lattice, but Flory-Huggins theory is actually not just limited to consideration of not just limited to a cubic lattice, other kinds of lattice geometries also are fine. So, let us say that component 1 solvent molecules, N1 molecules occupy N1 lattice cells, and next let us say that we add polymer molecules to this solvent to form our solution. So, for the polymer molecules here are represented by these orange circles connected through these black bars. Individual units of the polymer molecules are connected to each other through the bonds. So, the component 2, which is the solute in our case, is the polymer, and that also is represented on a lattice in this Flory-Huggins theory. So, as a representation here we have shown only 2 polymer molecules, but let us say for the general case, for the development of this theory, we have a total of N2 number of polymer molecules. So, one polymer molecule is basically one chain of polymer. So, N2 polymer molecules means N2 chains of polymer. And another detail is that for each polymer molecule or for each polymer chain we have X segments. So, the orange circles that we have here, these basically are referred to as segments in Flory-Huggins theory. So, for in this representative example we have 2 polymer chains each having 8 segments, but for the general case for the development of the theory we will consider N2 polymer molecules, and with each polymer molecule having X number of segments. So, if we combine the polymer with the solvent, what the theory assumes is that the solution that forms is can also be described on a lattice, and the nature of or the type of the lattice for the solvent molecules and the pure polymer molecules as well as the polymer solution, the type of lattice is identical or the same for all the 3 cases. So, that is one of the assumptions of this Flory-Huggins theory, which need not be very realistic, because strictly speaking the molecular arrangement in polymer, pure polymer or in pure solvent need not follow similar kind of lattice structure. So, in any case that is one of the assumptions, and so mixing the polymer N2 molecules of polymers and N1 molecules of the solvent gives us our polymer solution having N1 plus N2 molecules. So, in the case of solvent we have N1 molecules occupying N1 lattice cells. In the case of polymer we have N2 molecules occupying X times N2 lattice cells, because each molecule basically contains X segments. In the case of polymer, each segment occupies one lattice cell. So, we have X times N2 cells which are being occupied by X times N2 polymer segments. So, another assumption of this Flory-Huggins theory is that the volume of a given polymer segment and the volume of a solvent molecule, they are identical. So, volume of polymer segment and a volume of a solvent molecule shown here, these are assumed to be same in this Flory-Huggins theory. So, when we combine them, the polymer solution that forms will contain N1 molecules of solvent, N2 molecules of the polymer, but since each polymer molecule occupies X times or X number of cells, because it has X number of segments. So, the total number of lattice cells in the polymer solution that is formed. So, the total number of lattice cells that will be occupied is N1 plus X N2, where N1 lattice cells are occupied by the solvent molecules and X times N2 lattice cells are occupied by the different polymer segments that we have. So, with this kind of description we will now proceed to find out how the thermodynamic properties or property changes can be obtained for such cases. So, if we again go back to the quantities omega 1, omega 2 and omega 1 2, so if we look at these quantities omega 1 2 as well, So, omega 1 is pure solvent where we have N1 molecules placed on N1 cells of a lattice. So, since all the molecules are identical, there is only one way or one arrangement here. So, omega 1 again is 1, but in the case of polymer molecules, although all the polymer molecules again in this theory are also assumed to be identical or of the same length, but their connectivity actually leads to a situation where omega 2 actually is not unity, will have a value much higher than 1. So, although polymer molecules are identical, since the segments are connected in a given polymer chain, that actually leads to the possibility of multiple distinguishable arrangements, and omega 2, as we will see, will be much larger than 1. Similarly, when we have polymer solution, of course, omega 1 2 will be much larger than 1, but here again I mean, apart from the fact that we have two different types of molecules, again the polymer chains are also being connected internally, they can adopt different conformations, and that will further add to the different number of distinguishable arrangements. So, both omega 2 and omega 1 2 need to be calculated, and that is the essence of this Flory-Huggins theory, how the approach used to calculate these two quantities, and from there of course the entropy change of mixing can be calculated. So, as we discussed, the long chain nature of polymer molecules as well as the fact that the segments are connected to each other, that leads to multiple different conformational possibilities for the polymers, and hence the omega 2 and omega 1 2 are large. So, again let us just consider a illustrative example for the same thing. So, let us focus just at the pure polymer case, the lattice containing pure polymer molecules. So, in this representative case, this what shown here is one possible conformation that the two polymer molecules can have. Similarly, the two polymer molecules can also adopt different conformation that shown here, or the conformation adopted can change to something like this. So, these are just three sample or representative conformations of the polymer that are shown. There are many other conformations that are possible, and due to the fact that multiple conformations can be adopted by the polymer chains, the number of distinguishable arrangements of these chains on the lattice is also quite large. So, so that is why omega 2 will be much larger than 1, and similarly for the polymer solution also similar case is there. So, omega 1 2 also will be much larger than 1. So, so before we go ahead, in today's lecture we will focus on only one part of the Flory-Huggins theory, and that part deals with the case where we are considering the mixing of the solvent with the polymer as athermal mixing. So, athermal mixing is a mixing where the enthalpy change of mixing is 0. So, what we are assuming is that in athermal mixing the interactions again are similar to each other, or the interactions, the difference in interactions between polymer solvent and polymer polymer or solvent solvent, these different interactions are not that important, and ultimately the enthalpy of mixing is 0. So, this is something that is not very realistic, but to develop this theory as a starting point we will consider the case of athermal mixing of our polymer solution, where the enthalpy change is 0 and the complexity due to the interactions is not accounted for. But what we will do is in the next lecture we will incorporate some other terms which account for the interactions present, and take into the consideration the fact that enthalpy change of mixing actually is not 0. So, in today's discussion all that we are doing is trying to come up with an expression for the entropy change of mixing from what is called a purely combinatorial perspective. We are not taking into consideration any difference in interactions. So, so the discussion today is limited to the case of or assumption of athermal mixing, where the delta H of mixing is 0. In the next lecture we will relax that assumption and add extra terms to develop the complete theory. So, let us look at the polymer solution as our system, which again is a model where all the solvent molecules and polymer molecules are placed on a lattice. So, in this system we have, as we discussed, we have N1 plus N2 molecules. So, we have for each polymer molecule x segments are there. So, a total of x times N2 polymer segments are there. So, these are the individual polymer segments, and a total of x times n2 polymer segments are there. Total number of lattice cells is n1 plus x n2. So, n1 is number of molecules of solvent and x times n2 is the number of molecules of polymer segment, and one cell is occupied either by a solvent molecule or by a polymer segment. Now, our aim is to calculate an expression or develop an expression for omega 12. So, here what we will do is to develop an expression, we will consider that the lattice is initially empty and it is filled by first adding the polymer molecules to the lattice one by one, and then at the end adding all the solvent molecules to the remaining empty sites. So, as we are adding the polymer molecules one by one, we will also try to come up with an expression for the different possible arrangements that the polymer molecules can adopt, and using that we will try to come up with an expression for omega 12. So, for this stepwise addition of polymer molecules, let us say initially we consider lattice to be completely empty and we are trying to add the first polymer molecule to this lattice. So, again for each polymer molecule that is being added, the addition will be done segment by segment. So, the first segment of the first polymer molecule, when we try to add that, the entire lattice is empty and the entire lattice is available for adding this first segment of first polymer molecule. So, if we have n1 plus x n2 times a number of lattice cells available, so those many possibilities are there for placing the first segment of the first polymer molecule. Now, the next segment of this first polymer molecule, that cannot be arbitrarily placed anywhere, because it has to be connected to the first segment that was placed on the lattice. So, due to the connectivity of polymer chain, we see that already there is some restriction. So, the next segment can only be placed in one of the adjacent or neighboring cells of the first segment that has been placed. So, after placing the first segment of this first polymer molecule, the remaining x minus 1 segments, so total x segments are there. So, the remaining x minus 1 segments, they can only be placed in empty cells which are adjacent to the previously added segments, because they have to be connected to the previously added segments, so for the chain connectivity to be there. Next, for each segment of the chain, the individual number of possible arrangements that are there, that is counted or calculated. So, the individual number of possible placements for each segment is calculated, and for a polymer chain, the number of possible conformations that can be there for a given polymer chain, that will represent by this symbol nu in our discussion, and that is calculated simply by multiplying together all the different possible placements of all the segments that we have considered for that chain. So, just a continuous multiplication of the different possible placements for all the chain segments of a given chain, when they are multiplied together, that will give us the number of possible conformations that a given chain will adopt. And as the polymer molecules are added successively, the different number of possible conformations, each polymer molecule that is being added, how many conformations it can adopt, that is calculated. And finally, when all the polymer molecules have been added and the different possible arrangements that are there, they have been calculated, the remaining empty cells will be n1. So, and the remaining n1 solvent molecules will be added to those n1 cells. So, again the solvent molecules are indistinguishable. So, there is only one way to add the n1 solvent molecules to the remaining empty n1 cells of the lattice. So, only one distinguishable special arrangement for this solvent molecule addition will be there, because all the solvent molecules are identical. Next, let us try to calculate this quantity omega 12, that is our aim here, to calculate omega 12 as well as omega 2, and then to calculate the entropy change of mixing. So, this omega 12, based on our previous discussion, since we have a total of n2 number of polymer chains, the omega 12 actually can be simply written in this form, 1 by n2 factorial, and this symbol here, the symbol here basically is the symbol for a continuous product. So, just like capital sigma is a symbol for summation, this capital pi is symbol for continuous product. So, what this means is that we are multiplying nu 1 with nu 2 with nu 3 and so on with nu N2. So, all these nus which basically correspond to the different number of conformations of the individual polymer chains, all these nus are multiplied together in this term here, and then it is divided by N2 factorial, because at the end all the N2 polymer molecules in themselves are identical. So, we are not considering the polymer molecules to have different length or any different chemical identity. All the polymer molecules have the same number of segments and they are identical. So, to account for the overcounting due to the fact that polymer molecules themselves are identical, this factor N2 is used in the denominator here. Next, let us focus on this quantity nu. So, in this expression, in this continuous product that we have here, this zeta here, this zeta, that basically is a kind of an index for this product. So, zeta basically runs through all the different polymer chains that we have in our system. So, zeta equal to 1 corresponds to the first polymer chain that is added, zeta equal to 2 corresponds to the second polymer chain that we are adding to the lattice, and so on all the way up to N2, because we have N2 number of polymer chains. So, this will run up to N2. Now, the expression for nu zeta, that is important, because once we have that expression, that we can back substitute here and then try to simplify and come up with an expression for omega. So, for expression for zeta or nu zeta, basically a different number of conformations possible for the chain number zeta that is being added to our lattice. So, that is given by the expression that we have shown here. Here this quantity z is called the coordination number of the lattice. So, whatever lattice we are considering, we are showing as planar square lattice, but it is irrespective of the type of lattice, the only detail of the lattice that is important that comes into the theory, at least at this point, is the coordination number of the lattice. So, even if we have some other lattice, if we know the coordination number of the lattice, then we can just introduce that quantity as z in these expressions, and we will see that later on in the expression for the entropy change of mixing, this coordination number does not feature at all. So, in the final expression becomes independent of the type of lattice being considered. So, here actually we have 3 terms and each term has some physical meaning. So, the first term basically corresponds to the number of ways in which the first segment that you are adding of this chain number zeta, the number of ways in which the first segment can be placed in the lattice, that is this term. This second term corresponds to the number of ways in which the second segment can be placed of this chain number zeta in the lattice, and this actually is a product of actually x minus 2 terms. You see this power raised to the power x minus 2. So, there are x minus 2 terms here, and these correspond to the remaining addition of the remaining x minus 2 segments of the chain number zeta. So, we will not go into the detail of the these terms. The one thing to point out here is that in the derivation of this expression here, an assumption is made in the Flory-Higgins theory called the mean field assumption. So, what that assumption states is that when a given segment is added in a lattice, then it is assumed that the previously added segments are homogeneously distributed throughout the lattice. So, if a given polymer segment is being added, all the other segments that have already been added to the lattice, they are assumed to be uniformly distributed across the lattice, and that is the mean field assumption or mean field approximation of Flory-Higgins theory. So, using mean field approximation, actually the second term and this third term can be written. So, this mean field approximation which says that the segment distribution or polymer segment distribution is uniform throughout the polymer solution or the lattice, that kind of approximation is for a concentrated solution, that is a reasonable approximation, because you will have polymer chains and segments distributed almost throughout the solution. But for a dilute solution, that approximation is severely limiting, as we will notice or note later on. So, So, this nu zeta, the number of conformation of this zeta chain, that the expression that we have here, this expression can be simplified and the final expression that we obtain is shown here. Next, if we substitute the expression for nu zeta from the previous slide here, so the nu zeta that we had from the previous slide is this, a simplified version. We substitute that in the expression for omega 1 2, the resulting expression that we get is shown here. So, these expressions might seem a bit long, but we will see that later on after appropriate mathematical manipulations. All the final expression that we will get will be relatively simple. Mathematically it will be as simple as the expression that we got for an ideal solution, although the form will be slightly different. So, now again from this expression here, these terms can be taken out because these terms do not depend on the zeta over which the product is being taken. So, these terms can be taken outside, and if we take the terms outside, a power of n2 comes over all these terms, because this is these terms are actually getting multiplied n2 times if we expand this product. So, when we take them out, this term will get raised to the power n2 here, and this will remain inside the product because we have a zeta containing term here. So, in any case this is the expression that we get, and again now if we consider the case of pure polymer. So, apart from omega 1 2 whose expression we have obtained, the expression for omega 2, that is the number of possible arrangements for the pure polymer chains on the lattice, that is also something that we need to calculate, because that is it is not trivial to find that out. So, but since we have already obtained an expression for omega 1 2, get an expression for omega 2, which is that for a pure polymer, that becomes simple, because a similar kind of approach can be adopted as was done for this polymer solution case, where the polymer molecules are being added one by one, and just once the polymer molecules are being added successively, the different arrangements possible can be counted. So, similar approach can be used. The only difference here is that now the total x n2 polymer segments that we have, they are getting added to only x n2 lattice cells for the case of pure polymer. In the case of polymer solution, this x n2 polymer segments were being added to n1 plus x n2 lattice cells, whereas now for pure polymer they are getting added to this x n2 lattice cells. So, in this expression here, just replacing this term n, where this n is nothing but n1 plus x n2. So, if we replace this n by x n2, then we can just obtain an expression for omega 2. So, the expression for omega 2 that applies for the pure polymer is this, and again in this expression we can make certain simplifications. So, if we start from that expression and we rearrange the terms a bit. So, we take these terms outside, take this n2 in here, and this term these terms we have taken outside. So, the bracketed term that we have created just by rearranging the some of the other terms. So, the bracketed term basically can be further simplified. So, the bracketed term is again shown here or written here. So, it can be simplified to this form, okay. And again this is just simple mathematical manipulation. So, you can just work through it and verify that further simplification will lead to this expression, and the expression that we have obtained there, that expression which is shown here, that expression can again be further simplified if we take natural log, apply Stirling's approximation and do some mathematical manipulation. So, it can be shown that this term here is equal to this quantity x by e to the power x minus 1 to the whole to the power n2. So, now that we have simplified this term, the omega 2 which was a product of this term as well as this bracketed term. So, this bracketed term we have simplified in this form. So, finally, the expression for omega 2 becomes what shown here. So, we get a relatively simpler expression now. So, for omega 2 as we discussed, we get simplified expression like this. Omega 1 2 we are not going to the detailed mathematical manipulations here, but for omega 1 2 it can be shown again using some mathematical manipulations and application of again Stirling's approximation and so on. It can be shown that omega 1 2 is basically given by as can be given as a product of omega 2 and this bracketed quantity. Omega 1 which is the for the pure solvent, that's again just one, because for a pure solvent we have n1 identical solvent molecules which have to be placed on n1 lattice cells. So, there is only one possible arrangement. So, omega 1 is just 1. So, now for the combinatorial entropy term, this here, from the definition we have this delta S combinatorial as Boltzmann constant times natural log of this ratio. And if we substitute the expression for omega 1 2 as well as omega 2 and omega 1 from these expressions, if we substitute all of these here, so if we substitute all these 3 here, then we end up with this equation for our combinatorial entropy change. So, if we again take the natural log, then this expression that we have, this can be further simplified as shown here, and again some just taking the reciprocal of these terms inside the natural log. So, we are inverting these terms. So, here you see it is n1 by n and xn2 by n instead of n by n1 and n by xn2. So, if we invert these, then basically a minus sign will come outside. So, the expression for delta S combinatorial can be written like this. Now, these two quantities, this ratio as well as this ratio, these ratios if we represent by phi 1 and phi 2, then the expression for combinatorial entropy change of mixing according to Flory-Huggins theory will be given by this expression. And again if we wish to change from number of molecules to number of moles, then the Boltzmann constant will change to the universal gas constant. So, this is the expression for combinatorial entropy according to Flory-Huggins theory. Here the phi 1 and phi 2, if you notice carefully, the phi 1 and phi 2 which correspond to this ratio n1 by n and xn2 by n, these two are basically the volume fraction of the solvent. So, phi 1 is the volume fraction of the solvent and phi 2 is the volume fraction of the polymer in the solution. So, phi 1 is defined as n1 by n, which is n1 by n1 plus xn2, phi 2 is xn2 by n. So, if we recall the lattice model for our polymer solution, there we have n1 plus xn2 total number of cells, n1 cells are occupied by solvent molecules. So, the volume fraction of solvent in that kind of an arrangement will just be n1 by n1 plus xn2. So, that is what this phi 1 is. Similarly, for the polymer molecules actually occupy x times n2 cells, because each we have n2 polymer molecules and each polymer molecule occupies x number of cells because it contains x segments. So, there the volume fraction will simply be the number of cells occupied by total number of cells, which is again xn2 divided by n1 plus xn2. So, phi 1 and phi 2 as mentioned are the respective volume fraction of the solvent and the volume fraction of the solute or the polymer. So, we will conclude or stop this lecture here where we have developed an expression for the combinatorial entropy change of mixing, which purely depends on the different ways in which a polymer chain can arrange itself, or the different conformations the polymer chain can adopt, leading to entropy change of mixing. Apart from this, so here in this discussion we have completely ignored any interactions or difference in interactions. We said that for this part we are assuming athermal mixing, but in the next lecture what we will do is extend this theory to incorporate the effect of different interaction between the polymer molecules and the solvent molecules, and after incorporation of that effect of interactions, the final expression that we will obtain for the delta G or the Gibbs energy change of mixing, that will be the that will give us the Flory-Huggins equation for the Gibbs energy change of mixing.